Okay, this is the second tutorial in Physics 106. And in this tutorial, we're exploring what happens when a pulse reaches a boundary between two different springs that are made of different materials, of different uh, mass density, and that are connected together. And um, we are looking at a bunch of pictures that were taken at equal time intervals as a strobe photograph. And these are fairly primitive. They're from that textbook PSSC that was published in the 60s, but that's what Lillian was familiar with, and it serves our purpose. Now, we're looking at reflection and transmission at a boundary, and this is the boundary right here. Okay. The photographs below illustrate the behavior of two springs joined end to end when a pulse reaches the boundary between the springs. The snapshots were taken at equal time intervals. Describe what happens after the pulse reaches the boundary between the springs. Well, we see that the pulse comes in, and when it gets to the boundary, uh, an interesting thing happens. Part of the pulse transmits or continues on into the new spring, and part of the pulse is reflected back into the original spring. And so essentially, I get a splitting. The incident pulse splits into reflected and transmitted pulses. Okay. Uh, if we compare the widths of the incident and the transmitted pulses, we see that the incident pulse is wide. And down here in 8, uh, the width of the transmitted pulse is narrow. And so I'll use L to represent the width of the incident is greater than the width of the transmitted. Okay. Now compare the speed of the pulse in one spring to the speed of a pulse in another spring. And we want to make this comparison in two different ways. In the first case, we want to use the information contained in two or more snapshots. Well, let's look at snapshots 1 through 4. Um, if I look at the incident pulse, it goes from here to here during that time interval. And so it's covered about a third of the picture frame in that time period. Now, if I go down to pictures 7 through 10, that's the same time interval that we looked at above. But if we look at the transmitted pulse, it's only gone from here to there. I mean, it's barely covered 10% of the frame of the picture. And so we can see that the speed, um, the velocity of the incident is greater than the velocity of the transmitted. Now, we can also make the same determination just by looking at snapshot 8. Um, I like to think of these pulses in a different way. I think of the original pulse, the incident pulse, as the mother pulse. And that mother pulse comes into that boundary and dies. Okay. And in its death gives birth to twins Those twins are the transmitted pulse that goes scurrying into the other spring and the reflected pulse that bounces back into the original spring. And these twins were born at the same time, midnight, at the same place, the same hospital. And then they went scurrying on their merry way, the transmitted to the right and the reflected to the left. And you see that the transmitted pulse hasn't gotten very far from the hospital, from the birthplace, from the boundary in the time it took from when they were created to when we took this picture. The reflected pulse, on the other hand, got quite a ways away from its birthplace, from the boundary. And so I get the same answer that the velocity of the incident pulse um, is uh, is much bigger. In this case, the velocity of the reflected pulse is much bigger. Okay. Um, so if I could just pause here for a moment. This is probably something that you have never stayed awake at night worrying about. What happens to a pulse when it meets a boundary between two springs that for some reason were fused together? Um, but I want to point out that this is a problem that comes up time and time again in science and in physics in particular. And that is that whenever we have any kind of wave phenomena that reaches a boundary between a fast medium and a slow medium, uh, part of the energy gets transmitted into the new medium, and part of it reflects back into the old medium. And that's why we do things like matching impedances in your stereo system. If you have a mismatch in impedance in the components, what you'll find is that instead of the signal going straight through so that it sounds wonderful, you're going to find that part of that signal is reflected back, and only part of it goes forward. You also see this in, uh, say, if you go to the ocean and you happen to be looking over, uh, say, there's a little bay there and waves are rolling in. If there is an abrupt change in depth, if there's some sort of seawall underneath the water that changes the depth of the water from shallow to deep, what you'll find is that as the waves reach that point, they'll split, and some of the wave will reflect back, and some of the wave will continue onto the shore. This happens over and over again, so we would like to understand it. Um, In answering the questions below, assume that each spring has approximately uniform tension. How does the tension in one spring compare to the tension in the other spring? Well, we know that the speed of pulses in a spring or string is given by this formula here, where mu is the linear mass density, the mass of the spring divided by the length of the spring. I also know that the tension in the left spring has to equal the tension in the right spring. Well, how do I know that? Well, there's two ways I can argue this. If I use Newton's third law, those two springs are pulling on each other, and the left one can't pull on the right one any harder than the right one's pulling back on the left one. That's just Newton's third law. That's part of the same interaction. if you're not comfortable with Newton's third law, if you didn't take Physics 105 from me, let's use the second law. Suppose that these two springs are connected by a ring, and let's let that ring be one of those special massless rings that you can only buy in the basement of the physics building. Well, I know that by Newton's second law, that if the mass is zero for that ring, it doesn't matter what the acceleration is, it can be huge. The net force has to be zero. My free body diagram has to be balanced. And on that ring, I only have two forces. I have the right spring pulling to the right and the left spring pulling to the left. Those forces have to be equal. Well, what about the linear mass density of one spring compared to the other? Well, you can see, since the mass density is in the basement there, that the bigger the mass density, if this gets really, really big, my velocity gets really, really small. And so that means that the linear mass density of the left must be less than the linear mass density of the right. Or, this is going to be more useful, I can say the linear mass density of the fast has to be less than the linear mass density of the slow. That's really going to be helpful. Okay. Now, we're going to look now at what happens to the width of a pulse when it passes from one spring to another. And we want to uh, imagine that this is the boundary between these two springs that were shown in page one. And so that means this is going to be the fast side, and this is going to be the slow side over here. And ultimately, we want to know what happens to the width of a single pulse when it passes through that boundary. And the way we're going to do that is we're going to look instead at two separate pulses. And then eventually we're going to treat this pulse as the leading edge of a bigger pulse. And this second pulse we're going to treat as the trailing edge of that bigger pulse. But right now, let's just think of those as two separate pulses. And we're just going to look at what happens in transmission. We're not going to worry about the reflection on this page here. We're just going to worry about transmission. It says ignore the reflected pulses. Excuse me, I still have that cold. I'm still having a hard time getting through the night. Imagine that you measure the time interval that starts when the crest of the first pulse reaches point X and ends when the crest of the second pulse reaches that same point. So, in other words, um, you stand right here with a stopwatch. And when this pulse gets to you, you start your clock. And when this pulse gets to you at X, you stop. And let's say that that time interval, I'm making this number up, is 2 seconds. 2 seconds. Okay. Also imagine that one of your partners, a friend, is at Y. Okay. And they make the same measurement for the transmitted pulses. With the time interval for the incident pulses, that was the 2 seconds at point X, be greater than, less than, or equal to the time interval for the transmitted pulses. In other words, your friend here, are they going to measure something smaller than 2 seconds, equal to 2 seconds, or bigger than 2 seconds? And I hope you can see that it's got to be equal to, okay? And we're given a hint here that is very useful. Imagine that you have a second friend, Or even more unimaginable, imagine that I have two friends. Okay, that seems unlikely. But this second friend is right at the boundary. Now, I think we can agree that if the timing between these two pulses was 2 seconds for you at X, it's also going to be 2 seconds for your friend at the boundary. Okay, because this pulse reaches the boundary and this one was 2 seconds behind it at X. It's still going to be 2 seconds behind it at the boundary. They're in the same spring. Okay. So this friend here at the boundary is going to measure 2 seconds between those two pulses. Well, what that means is that the first pulse left the boundary 2 seconds before the second pulse. And again, they're both in the same spring. It's a different spring than they started out in, but now they're both in the slow spring. Um, and the second pulse is starting 2 seconds later. It's going to arrive at Y 2 seconds later. Okay. So let's say the second pulse leaves boundary uh, with same time delay as at X. Okay. What about the distance between the transmitted crest and the incident crest? Well, the transmitted crest, let's think about those pulses leaving the boundary. Okay. Um, they arrive 2 seconds apart, but one takes off towards point Y, and the other one doesn't leave until 2 seconds later. But the first pulse hasn't gotten very far because it's a slow spring. Things are moving slow in that spring. In those 2 seconds, it hasn't gotten very far. So the distance between them has to be less than um, the first pulse doesn't travel very far before second pulse leaves boundary. Okay. Now, I'm going to talk more about this in lecture, but let's imagine for a moment that we had a magic school bus. Okay. And this school bus is magic in that it can stretch or it can compress. And let's suppose that it's going in a fast medium like pavement, and then it reaches this boundary between a very rutted, muddy road. And what we find is that the front of the bus gets to the mud first and slows down, while the back of the bus is still going fast on the pavement. And so when the whole bus gets onto uh, the muddy road, it's shorter. Okay, it's shorter. Um, is the time it takes a single incident pulse to pass point X greater than, less than, or equal to the time it takes a single transmitted pulse to pass by point Y? Well, here's where we think of this pulse one and pulse two as the start and the leading edge and the trailing edge of a single pulse. There's my single pulse right there. And if the timing for these guys is the same at Y as it is at X, the time for a single pulse to pass would be the same. So this would be equal to. So let first pulse be leading edge of single pulse. Whoops. And let second pulse be the trailing edge. Having a hard time writing. Explain how the change in width of the pulse as it passes from the first spring to the second is a direct consequence in the speed of the two springs. Yeah, we've done that. So what we would see when these two pulses got over into the slow spring is that they would be narrower and they would be closer together. Okay, so if this is pulse one and this is pulse two, this would be pulse one prime and this would be pulse two prime, the transmitted pulses. Okay, now reflection and transmission at a boundary revisited. So here we've got the same two pulses where this is the fast pulse over here and this is the slow pulse there, or slow spring rather. Um, but this time the incident pulse, the mother pulse, is coming from the slow side. And we're told that the springs in the photograph at the right are the same as on the first page, okay? But now the pulse approaching the boundary between the springs is from the right. After the trailing edge of the incident pulse has reached the boundary, will there be a reflected pulse? Well, um, everything that we've seen so far suggests that there will be. And the question is, on which side of the spring will the reflected pulse be located? And how will its width compare to the width of the incident pulse? Well, now let's go back to this reasoning here and think about a reflected pulse. If it took 2 seconds between the first pulse and the second pulse getting to point X, then it's going to take 2 seconds between the first pulse reaching the boundary and bouncing, and the second pulse reaching the boundary and bouncing. And since they're going the same speed coming back as they were going into the boundary, there's going to be exactly the same width. So um, it's going to be on the same side and it will have the same width. Okay. So the speed of the reflected pulse is going to be equal to the speed of the incident pulse. And so they will have the same width. Okay. Now, why do I say they're on the same side? Well, if I go back to the front page, we see that when we came in on the, um, I'm going to call it the fast side, and we hit the slow spring, um, the reflected pulse inverted, as if we had hit a fixed end. It looked very much like hitting a fixed end where the spring is tied to the wall. And in the other case that we're considering on page 3, we're going from a slow medium, I could also say a heavy spring, to a fast medium. I could say that's the light spring. And in that case, this boundary right here is going to act like a free end. Okay, so I'm going to say acts like a free end. How will the transmitted pulse compare to the incident pulse? Well, um, I know that if going from fast to slow makes the pulse get narrower, that going from slow to fast will make it wider. So in this case, the transmitted width will be greater than the incident. And so, in the space below the photograph, make a sketch that shows the shape of the springs at an instant after the incident pulse is completely transmitted. Your sketch should illustrate the relative widths of the pulses, the relative distances from the boundary, as well as which side of the spring each pulse is on. So, if this is the boundary, I'm going to have a pulse going back that is on the same side, the same width going that way, reflected. And over here, I'm going to have something further from the boundary that's wider going that way. Now, I can talk about whether they're on the same side of the spring or the opposite side of the spring, and I can talk about the relative lengths. Um, but what I can't talk about is this amplitude. Okay, that's just too messy. There's just too much physics involved there. I can say, without any question, that the reflected pulse is always going to be a little bit smaller than the incident pulse because they're on the same spring and some of the energy went into the other spring. But, this transmitted pulse, sometimes it can be larger than the incident, sometimes it can be smaller, sometimes it can be the same. I can't make any predictions, and I wouldn't ask you any questions about that on an exam. Um, there's a series of photographs that show this. It's pretty blurry. What I've got is a Xerox of a Xerox of a Xerox. It looks like this. So take my word for it. Our prediction is correct. Let's build a model for reflection at a boundary. We have observed that reflection occurs when a pulse reaches the boundary between two springs. That is, where there is an abrupt change in the medium. We would like to be able to predict whether the boundary will act more like a fixed end or more like a free end. In the situation illustrated in section 1 on the first page, are the incident and reflected pulses on the same side or on the opposite side? They're on the opposite side. On the basis of this observation, does it appear that the reflection at the boundary was acting more like a fixed end or a free end? More like a fixed end. Okay, last page. Which of the following quantities are different for the two sides of the boundary? Well, the tension is the same. The linear mass density is different, and the wave speed is different. Which of the above quantities could you use to predict whether the boundary will act more like a fixed end or a free end? Well, clearly, that one's not going to be helpful because that's the same on both. Um, so they suggest that we consider limiting cases. So uh, let's take the case where I've got fishing line And that's connected to a heavy chain, maybe made of lead. Okay. If I have a pulse coming in on the fishing line, that's going to see this boundary as a fixed end. That doesn't want to move. And so that's going to reflect back inverted. On the other hand, if I send in a pulse on the heavy chain and it meets this fishing line, that's acting very much like a free end. And so my reflected is going to come back on the same side. So describe how you could predict whether the reflected pulse will be on the same side of the spring as the incident pulse or whether it's on the opposite side. So if you're going from fast to slow, or in other words, light to heavy, that acts like a fixed end and inverts. If, on the other hand, you're going from slow to fast, or equivalently, heavy to light, that's going to act like a free end. Does doesn't invert. Describe how you could predict whether the transmitted pulse will be on the same side of the spring as the incident pulse or whether it will be on the opposite side. Well, this is really, really easy, and that is the transmitted pulse is always on same side as incident pulse. And the key word there is always, every stinking time. So just to make sure that we all got the message, imagine that a pulse on a spring is approaching a boundary. Would the boundary act more like a fixed end or a free end if the spring is connected to a very massive chain? That's going to act like a fixed end. And if it's a very light fishing line, that's going to act like a free end. Okay, that's the end of the tutorial. Uh, we are going to stop the recording.